Alright, so in the previous video we talked about the photoelectric effect, we talked about de Broglie wavelength of electrons, and we talked about the wave function and how photovoltaic cells work. But then Niels Bohr was working on the atom, which I think you guys talked about in HESSEL, maybe even in chemistry, and figured out that the electrons can only be within certain orbits. And it can't be within any orbit, so that basically the energy of the electron is quantized and that it can only be within certain orbits, as I said. And so we have the next two equations from the data booklet are related to Bohr's model of the atom. And then we can jump from here, again making reference back to de Broglie wavelength, and then move into Schrodinger and the wave function of electrons. So first, staring us right in the face here is this equation. It says the energy of an orbit is the energy required to ionize an electron to remove it, it says given to the following equation, something called the Rydberg constant in joules. That's the same equation as on the data booklet. On the data booklet, they give the formula in electron volts, and so pretty much they're just converting that Rydberg constant in joules to electron volts and saying it's 13.6 electron volts. And so the energy to ionize an electron, again, that's what the E is, the energy to ionize the electron to remove it, that's what E is. It's negative 13.6 over n squared electron volts, where n is the number of the orbital, starting with 1 on the center, 2, 3, etc. The energy is negative because it's kind of like a relative, it's measured relatively, whereas if we consider the energy emitted by an electron in the form of a photon to be positive, then the absorption energy, the energy that the electron would absorb in order to be ionized, is taken as negative. That's why it's negative. Okay, there's another equation that even though we're talking about the Bohr model is not actually on this sheet, and it's the quantization of the angular momentum of an electron. So angular momentum is given as mvr, and what Bohr said is that the angular momentum is quantized, so we're going to bring in Planck's constant. And so we have mvr, the angular momentum of an electron, is the n, the shell number, 1, 2, 3, etc., times Planck's constant over 2 pi. And so there's the quantization. The Planck's constant in there brings in the quantization of the angular momentum. So yeah, those guys are on the data booklet. Those are equations 3 and 4 under subtopic 12.1. Now, I mentioned that de Broglie was going to come into this, the de Broglie wavelength of the electron itself, and it turns out that there's another thing about the electron orbitals. So the electrons, they'll only occupy orbitals such that the circumference of the orbital of the circle allows a whole number of integral wavelengths. So you have to fit a whole number of wavelengths into that circle, as if like they were, as if the electron were a wave, as that you have to fit whole waves into the size of that orbital. But we can take this a step further with regards to the wave function, the wave nature of the electron, and it's not just that the orbitals have to hold a whole number, an integral number of electrons. It's that the fact that an electron acts like a wave totally matters in terms of where the electron can be found, where you can locate it, what is its momentum, and these things actually come into probabilities. Like instead of just like pinpointing, pinning down a certain spot and being like, oh, the electron's going to be right there at this time. Ding, got it. That's not the way it works. It's rather that in a particular area, you have a greater chance of finding the electron as opposed to some other area. And this, though, is not the Bohr model of the atom. It's actually built upon the Bohr model of the atom. It is the Schrodinger model of the atom. And this is where what's called the wave function comes in. That's also going to be the next equation in the data booklet. but that is a separate review sheet, so I'm going to close this video. It's a short one, and I'm going to start a new one. Maybe not. I think maybe I can bring in the next review sheet without stopping this video. Let me give it a go. Okay, I did it. I inserted documents after the fact. So let's continue by talking about Schrödinger and the wave function. Alright, so the electron and every particle has what's called a wave function, and based on its wave function, you can figure out the probability of finding that particle, for instance, the electron around a hydrogen atom. Now, there's one formula here that says that the probability, and it says P is a function of R. I'm not in the SOCOS book, they refer to position and time. That's how I learned it. And I'm not finding anything that says otherwise, so I'm assuming that R, I keep on making reference to R and you don't know what I'm talking about. Let me write it down. So the probability of finding a particle is the square of its wave function psi, and the probability of finding a particle within a certain volume delta V. So that delta V is a certain volume that you're looking at, and it's the square of the wave function. So pretty much what this equation tells you is that the probability of finding the particle is proportional to the square of its wave function. I think it actually says that here. Yeah, it says that. It says psi times psi is the probability of finding the particle at that position in time. I thought it said something about proportional. Maybe that was just in my head. And if you're saying, well, what does that mean, the square of the wave function? The wave functions themselves are really complicated, and you don't need to dive into those, but just know that the probability of finding the particle is proportional to the square of the wave function. Times, of course, the volume. Times that the delta V is the volume of the space in which that you're looking at. But since we're talking probabilities, that means there's a certain uncertainty in locating that particle, in knowing its position, knowing its momentum, and knowing its energy. And that right there is an important point. You can really kind of get lost in the weeds when talking about probability functions, but it's more the notion of probability means that, it's kind of like, well, is it probable or improbable? Do you have a high likelihood, or do you have a low likelihood? Which is, again, we're talking about like certainty or uncertainty of these of determining information. And so for uncertainty, that takes us to our last two equations in subtopic 12.1, and we also have the equations over here for that uncertainty principle for energy and time and position and momentum. So right off the bat, I see that whoever made this sheet makes reference to h bar. H bar is just h over 2 pi. And I rewrote the expressions, here they are on the review sheet, but I rewrote them as they're written in the data booklet. They use h instead of h bar. But h bar is just h over 2 pi, so it's really not a big deal. So making reference to the wave equation before and how it represents the probability of finding an electron, that gets to this first expression here. They actually listed the position and momentum expression first in the data booklet, and that's that the uncertainty on position times the uncertainty on momentum is greater than or equal to h over 4 pi. So that's, which is a constant. So pretty much the interpretation of that is that you can't know both the position and the momentum of the particle precisely. You either know the position precisely but not the momentum, or you know the momentum precisely but not the position. And that's just a function of the wave equation of the probability density. And then another version of that is the energy of a system, or to know the energy state, it can last for a short period of time. Or rather, I should say that if the energy, as it says in the review sheet. Why can't I think of that word? It says the energy state only lasts for a brief period of time. Its energy is uncertain. So if if the time is very small, like if your delta t is very small, then your uncertainty, your delta e, is very large, on the in terms of the knowing the energy state. I remember learning about this when it comes to particle physics and how particles like quarks that are not allowed to exist by themselves in nature that have fractional charge, how those particles are detected by themselves if they're not allowed to exist by themselves in nature, if they form up to form other particles with whole numbers of charge. And my understanding is that when particles are collided in a particle collider, the quarks exist by themselves for such a small amount of time, for such a small delta t, that something about the uncertainty in their energy state allows them to be detected. I'm not sure why that's true, but I remember learning about that a while ago. I want to go back to the change in position, the uncertainty in position times the uncertainty in momentum equation. And there's an application of that equation, that delta x delta p greater than or equal to h over 4 pi, which is called electron in a box, and it pops up a lot. And so I just wanted to kind of walk through that as an application of this equation. So yeah, electron confined to a one-dimensional line of length L, and so maybe that'd be like maybe the diameter of a hydrogen atom or something. So the uncertainty in position will be like the radius will be like L over 2. So yeah, here's an application of that, saying that again L is the diameter of, say, like a hydrogen atom, so that the delta x, the relative, like where could the electron be, is bounded by that. So delta x would be L over 2, like the radius of the atom. And so if we say that delta x delta p is approximately h over 4 pi, then delta p is h over 4 pi delta x. And we said that delta x is about L over 2, so then we get that the delta p, change in the uncertainty in the momentum, is h over 2 pi times the 2 pi L. We know that kinetic energy is momentum squared over 2 times the mass, which is roughly the change in momentum squared over 2 times the mass. We know that change in momentum, delta p, is h over 2 pi L, so if we slip that in for delta p, we get kinetic energy of an electron in a hydrogen atom is h squared over 8 pi squared ml squared, where L is the diameter of the atom. And if we throw numbers in there, you actually do get a reasonable estimate for the kinetic energy of the electron. You get 4 electron volts. I'll save you all the numbers. But when they talk about this, in this problem, this is called electron in a box. That's a electron in a box. I remember when I took nuclear physics, I had to derive the equations for electron in a box, but we had to start with the Schrodinger wave equation. And so there, just as an application of that. One aspect of this probability function of position and momentum is that if you have a particle that needs to cross a barrier, like an energy barrier, it's possible to cross the tunnel through that barrier. It's not impossible, but it depends on the size of the energy barrier and the energy of your particle. But it's all a question of probabilities. Like, for instance, if you have an electron that is in orbit around a proton, like for hydrogen, it's highly probable that that electron is within 1 times 10 to the negative 10 meters of that proton. But it's not impossible that the electron is currently out orbiting at the distance of Pluto, that Pluto orbits around the sun. It's ridiculously improbable, but it's not impossible. So it's all a question of probabilities. But this tunneling effect is, works again for small particles like electrons. What's neat though is that if you pushed on a wall, like for instance, if you pushed on a wall all day, you would have pretty much near zero probability of passing through that wall. But if you pushed on a wall literally forever, for infinity, then you have a 100% chance of walking through the wall. But of course, we're talking about infinity. So yeah, it's not happening. Okay, there's one other aspect which I really do think is just a simple application of E equals mc squared, but they stuck it in topic 12, so I will include it. So here we have antimatter, annihilation, and pair production. I didn't want to actually change the size of the page itself. I'm going to zoom in on the page. There we go. And so antimatter, it says antiparticles have opposite charge, baryon number, lepton number, and strangeness. But pretty much antimatter, in a nutshell, everything about them is the same except the big deal is that they have opposite charge. I don't know that we're going to really run into baryon number and lepton number, but there you go. And then it's possible to take two particles, a particle and its antiparticle, and annihilate each other and create energy, and that energy is created in the form of photons, usually gamma particles. But the energy that's produced is linked to the mass of the particles that made them by, of course, E equals mc squared. And there's the notion of the question of how is there anything at all. They think that the Big Bang was actually a quantum fluctuation and imbalance in pair production and pair annihilation, such that more matter was created than antimatter. And so just as you can annihilate two particles and create two gamma photons, you can also turn a gamma photon into a pair of particles. It's called pair production. And in which an actual single photon can produce two particles. It's called the pair production. And the photon doesn't have to have exactly the amount, it has to have at least the amount of energy to create the mass of the particles. If it has more than that, that extra energy is turned into the kinetic energy of the particles. And that covers that, and that is the end of 12.1. Next video will be 12.2.